Hey there, in this video we're talking about polymorphism in the context of C++ programming. And this covers sections 15.6 to 15.8 in the Gaddis C++ book. So before you watch this, we're assuming that you've watched the prior video on inheritance in an object-oriented programming language. And again, that allows us to build families of related object classes in what we call a class hierarchy. Now, what polymorphism gives us, building upon that, is it gives us a way for code to very easily handle different types of objects in a hierarchy like that and automatically call the correct redefined functions for each different type. So this is super important. It's one of the top 3 items that object-oriented programming gives you as a feature. So let's get into this. So what is polymorphism exactly? It's a way for object pointers or references to refer to objects of many different types in a class hierarchy of inherited types. And once you have a reference or a pointer like that, you can then call the correct redefined member functions automatically for whatever type is referenced with no additional work from the part of the application programmer. So we can kind of reflect on this big idea by comparing it to the biological term. Polymorphism is actually a word from biology that we've borrowed here. And so if we look up that word in the Cambridge Dictionary, what it says is a polymorph, as a noun, is an animal or an organism that can exist in many different forms. So as a couple of examples of that, of polymorphism in biology, male and female ducks have very different appearances, totally different colorings. Obviously, they're the same species, but if you didn't know that, you might not realize that they are the same species because male and female ducks look so totally different in their feather coloring. To pick another example from the world of birds, Darwin's finches in the Galapagos Islands are very famous. They're one species, but a baby bird of that species comes out either with a very long, spiky bill that allows them to puncture through the fruit at the top of a cactus plant, or they come out with a very strong, short bill that allows them to tear up the cactus base, and that's what they use for their food. So again, it's really just one species, and it's effectively random for any particular baby finch which version it comes out as. You never get bills in the middle. They're either very long or they're very strong and short. But it is just one species that comes out in these 2 radically different forms and therefore has 2 totally different behaviors on how they feed themselves. And there's a bunch of other examples like that in both the animal kingdom and plant kingdom as well. Now, as another place that we could reflect on this, if you're familiar with the fantasy role-playing game Dungeons & Dragons, in D&D, there's a classic spell called Polymorph. And what that allows you to do if you cast it is you can turn a human into a frog or a snake or a pig or something like that. And it's really the same person. They've just taken on a different type of form because of this spell, and then they have to deal with that, which is kind of interesting. Okay, so polymorphism, kind of like that, dealing with one kind of thing that comes at us in a bunch of different forms is the idea. So here's the first step if you want to make that happen. You can define a pointer to a base class object in a hierarchy and use it to store the address to any derived class object in the hierarchy. So here's an example of that. Based on the examples in our prior lecture, you can make a graded activity pointer, call it exam, and then you can make a new, here we're using dynamic memory allocation, you can make a new pass-fail exam, get that address, and store it in the graded activity pointer. Now, if you remember from last time, graded activity is our parent class at the top of the hierarchy, and pass-fail exam is one of the child classes that are descended from that. So you're making a new one of the child class objects, taking the address and storing in a pointer of the type of the base class, the parent class at the top. Now, if you think about that, and you think back to what we said in chapter 9, when we were first talking about pointers, we said, you can't do that. That was one of the things that was specifically prohibited back in chapter 9, is you can't take the address of one type of thing and assign it, store it in a pointer of a different type of thing. We were very clear about that. C++ is a strongly typed language, and C++ wants to be very careful that you don't accidentally mix the types and then screw up something like pointer arithmetic, where it's really important that they know the size of this type versus this type when you step up through the memory system. So that feels like a violation of that basic principle from back in chapter 9. But think about this. What we said in the last video is, what inheritance gives us is that the child class is a version of the parent class. The child class actually is one of the types of the parent class. So in this example here, if I were to ask pass, fail, exam, is it a graded activity? Well, the answer is yes. A pass, fail exam is a special type of graded activity. So conceptually, at least, this makes sense that when you make a new pass, fail exam, you do have a graded activity. And that's why it makes sense, and C++ will actually allow you in this one specific case in a class hierarchy to store that in the base class pointer type. Okay, so at this point, once you realize that that's permissible, we have a way of having one type of pointer that could possibly refer to a bunch of different object types. So if I'm an application programmer working in a function and I get a graded activity pointer or reference, well, that actually could have a pointer that could have an address to a graded activity, to a pass-fail activity, to a pass-fail exam like this example, to a final exam. All of those things are possible based on the one graded activity pointer type. So one pointer type that could be pointing to a bunch of different subtypes of that parent class. Okay, so that's pretty powerful already. Now, the next thing is when you take that pointer and you start calling functions on that object type, and you can do that as long as it's one of the functions that are recognized by the parent class. The question is, knowing that I might have redefined some of those functions in the child classes, which version of the redefined function gets called? The version from the parent class or the version from the child class? Well, there's two different options. Let's look at both of them. So the first option is what's called static binding. And in C++, this is the default behavior where the redefined functions being called from a pointer, in this kind of situation, a pointer or reference, the redefined functions call the version of the function that's defined by the explicit pointer type, probably the parent class in our example. So in our example here, if you take that exam pointer, we're using the arrow syntax there, and call the getLetterGrade function, well, exam was explicitly defined at the outset as a graded activity pointer, the parent class. And therefore, what would normally happen here is you would call the graded activity the parent class version of that function. So static binding calls whatever the pointer type actually is, the parent class. Now, the reason why that's the default in C++ is this is very easy for the compiler. It can just look at the type of the pointer when it was declared, which for us would be graded activity pointer. You can fix it at compile time. There isn't any extra work the processor has to do when the program's running, because all that linkage is set when you compiled it to an object code. And it's all set as soon as you compile it. Very easy, right? There's only one thing that's going to be called. There's no variation to it. Super simple. But maybe that's not what you want. So the other option is called dynamic binding. And that's a process where the system, while the program's actually running, is going to track each type of underlying object and call the correct redefined functions for each. So in our example, if I have that exam pointer, and again, I call the getLetterGrade function, this is the exact same code, but if I have dynamic binding happening, it's going to do a little bit extra work. It's going to dig into that underlying object, find out what it really is, and in our example, it's actually a pass-fail exam, and then call the version of the redefined function just for that object, which is probably the child class redefined version of that function. Now, the reason why this is not the default is that this requires extra processing to be performed at runtime while your program is actually live. So the system will have to keep a table of every single different object that was ever created, exactly what type it is, what type of pointer is pointing to it, look that up, keep track of all the different versions of the redefined functions so that it can jump into and call the correct one each time. So extra work, it's going to take extra memory for that kind of table lookup process. The program's going to be a tiny bit slower. You probably won't notice it, but it is a tiny bit slower because of that extra work. So C++ is not going to do this extra work unless you tag the prototype to the function with the keyword virtual. You would do that in the parent class prototype, the first time you ever prototyped that function that's going to be redefined like that, and you put this keyword virtual as the first thing in the prototype to tell the system to do this extra work. Now, I will say, if you go to a different language, they might make a different choice about what the default is between these two options. Again, static binding or dynamic binding. For example, if you're working in Java, they pick the opposite. In Java, dynamic binding is the default that happens normally, and Java says, well, you know, if you have redefined functions, you probably want the appropriate one. Otherwise, why did you redefine the functions in the first place? And it would be special if you wanted to use static binding. And if you want that, you have to prefix the functions with the keyword final. That would be in Java again. You do the special thing for static. But in C++, we tend to lean in the direction of do the least amount of work, make it as fast and efficient as possible. And if you want more work, the programmer has to ask for it. So that's why this virtual keyword is used for us. Okay, so here's an example where that happens. If we take the graded activity parent class from last time, and this is almost exactly what you see here on screen, it's got a single member variable called score. It has a couple of constructors. It has an accessor and mutator. But the thing that we were really focused on is interesting is the function that's prototyped at the bottom here, the getLetterGrade function. And you can see that compared to last time, we've made one tiny little change down on line 27. That is, we've tagged that function with this virtual keyword that we were talking about. And so now having done that, throughout the class hierarchy, if you access child objects from a pointer or a reference, now it's going to do this extra work, and it's going to call the child class, the appropriate child class redefined version of getLetterGrade, and not necessarily the parent class version all the time. So here is the books out of the Gaddis book, program 1513, where this happens. And you can see in the main function here, they make two separate different types of objects. On line 12, they're making a graded activity object. Again, that's the parent class type. And then on line 17, they're declaring a pass-fail exam object. And again, that's one of the child classes. What's going to happen in a second, if you look at the prototype on line 7, is there's this function called displayGrade that takes in as an argument a graded activity pointer. And remember, you can pass in the address to an actual graded activity, or you can pass in the address to a pass-fail exam, because again, a pass-fail exam is a graded activity. So you can pass in any one of these things to a function like that. And that's what happens first on line 21. They're passing in the address to test1, which is the graded activity object. And then on line 23, you can also pass in the address to the pass-fail exam object. And either one of those is perfectly acceptable here. Great. So on the next slide, we'll look at the actual code of that function. And of course, the point here is basically to print on the screen your score, your numeric score, as well as your letter grade in any kind of situation. So in comes the graded activity pointer. And again, that could have been a graded activity reference. This would work exactly the same. References and pointers are basically the same thing under the hood. And what happens here is lines 36, 37, it says the activity's numeric score is activity arrow get score. And remember, get score is an accessor that was defined in the parent class. So all of the different child classes all share that same accessor, and it makes sense you can call that and see the numeric score on the screen. And then on lines 38, 39, it's printing out the activity's letter grade is activity arrow get letter grade. And remember, get letter grade was redefined. So what happens here, and which is super, super nice, this is the essence of polymorphism right here on line 39, is that if that activity pointer is really pointing at a graded activity type object, then it's going to look up that version of get letter grade and print out either A, B, C, D, or F. That's the version from the parent class. But if the activity pointer is actually referencing a child class like pass, fail, exam, then this exact same line calls the redefined version just for that, the version that prints out either a P or an F for passing or failing. So what appears to be one line of code on line 39 could jump us into a bunch of different versions of the redefined get letter grade, the correct one for whatever object you're really referring to. And again, it happens automatically. The application programmer that's working on this code right here doesn't even have to think about it. There's no if-else statement to make a choice. There's no switch statement. The system just automatically figures it out by itself because of polymorphism. So that's super powerful. This is a really important example that we should probably look at in the IDE. So looking at this example, I've gone into the Gaddis lecture code for chapter 15. I've gone into a folder they've got labeled graded activity version 3. I've pulled that on my desktop. So we're going to build this project here. Got a whole bunch of files, of course. You have all the header files for the whole class hierarchy, these 3 header files. You have the implementation files for each of those classes. And then you actually have 4 different applications here. We're just going to be building program 13 at the moment. We're interested in that. So to make this happen, I have to start up dev C++ is what I'll do as usual. And I'm going to have to make a project because it is a multi-file project, obviously, like it always is. So making a project here, console application that I'll call display grades is what we're interested in. Put it in that folder, of course, so standard process. Now it's giving me a main function here. I don't care about that because we already have a pre-built application, so I'll just get rid of this main function. So I do not save it. And just get rid of that right there. But what I do want to do is I want to add all of those files. So so for convenience, I'm going to add all the header files. I definitely need to add the implementations to all of the classes in the hierarchy that I'm dealing with. And then I'll also include the application for program 513. So once I have that here, I could look at that main application we've been talking about. Again, just exactly what we saw in the lecture there. I can hit compile. It's going to build all of those things. I'm going to get a whole bunch of files, of course, because all of the CPP files got converted into .o files plus some other stuff. The important thing is I now have displaygrades.exe, and I can run that. Again, here are the 2 different objects that we made, and here is the display grade function. So we'll just run that, see if it works like we expect. And here's the output. And you can see there that with this display grade function, the first test that actually was a graded activity, it's saying the numeric score was 88 and the activity's letter grade is B. Okay. And then the second one that was actually a pass-fail exam, it's saying the activity's numeric score is 75. Remember, it was a 100-question test and they missed 25. So their grade is actually 75, and this activity's letter grade is P. And so remember, that's the result of calling the redefined version that only reports on pass-fail status for get letter grade. So again, looking at line 39, that one line of code has called 2 different versions of the same function depending on what the underlying object is. Just to really nail that home, let's step through this in the debugger. So I will set a breakpoint right here. I'll just run the same thing again, one line at a time. So we make the 2 objects on those lines there, And we're going to call display grade the first time with that first object, which is graded activity. So I'll go into this function, and of course this function prints out the score. Great. Okay, and then it's about to call getLetterGrade, so I'm going to click into function here and see which version of getLetterGrade am I going to jump into. And what you'll see is, okay, this sent me to the graded activity version of getLetterGrade, because again, that first object is really a graded activity object. And so this is the code here that determines should this be an A, B, C, D, or F grade. Of course, remember that was an 88, so we're going to discover that that really ought to be a B, and we jump back here. We print it out, right? And just looking at the console. So at this point, we have printed out the status for that first test, which was actually a graded activity, and we got the letter B there. Let me just get this out of the way here. So now, over in the code, we're about to call display grade the second time. Jump in there with what's really a pass-fail exam, and we'll print out the score, okay. And we're about to call getLetterGrade. Where is it going to send us now? And you can see we've jumped into the pass-fail activities version of getLetterGrade. And here is where it's going to determine should I send back a P or an F. And of course this is getting a 75% result, so that's going to be a P here. And we jump back and we do the printing. And you can see at this point we have printed out the second one, with it's giving us a P letter grade. So again, that one line of code on line 39 has sent us potentially to two different versions of the same function, and that's polymorphism, right? We didn't need to deal with it. The actual application programmer didn't need to add any extra code around 39. Again, there's no if-else decision there. It just happens automatically, and that's the magic of polymorphism. And of course, the program's about to end here when you get out of the main function. I'll do one more thing. So hypothetically, if we go back to the top level base class, which is graded activity, if I look in the header file with the prototypes, remember what allowed that to happen, what turned on the dynamic binding was this virtual keyword in the prototype to getLetterGrade, the first time we ever saw that. So let's just think about what if that wasn't there. If I go in line 27 here and just take out the virtual, now I'm going to have to save this file, and you might want to look carefully here. I'm going to have to rebuild all of those CPP files because they all refer back to this graded activity.h that I'm looking at right now. So in Dev C++, I have to be careful not just to hit compile again, but I have to hit rebuild all to go in and actually recompile all the CPP files and remake all the .o files. Otherwise, it would just do one and glue all the existing .o files together. So I'll hit rebuild all, and it's going to rebuild all that stuff. And now when, again, I might as well look at the code here. And now when I run this, I see this. I see the report for the first test is 88 for a B, and the report for the second test is 75 for a C. Right? Now it's not jumping into, for the second test, it's not jumping into the redefined version that gives you a P or an F. What's happening now, without the virtual, now we've got static binding happening. And what happens is when you get in this display grade function, you get down to line 39, what's happening is it doesn't have the lookup table. It doesn't care what the underlying type of object is. It's just saying, hey, what type is activity? Looking here at the prototype, that's a graded activity pointer. So you're going to get the graded activity version of getLetterGrade. That's what you're going to get. And I'm not going to pay attention to any redefined functions. And again, that happens a little bit faster. It's a little bit easier for the compiler to figure out. It's kind of just obvious on the page here, but probably not what you actually wanted to happen. So at least hopefully that can highlight for you the difference between the static binding that we're looking at right this second versus the dynamic binding. And for the dynamic binding, you did need the virtual keyword. Okay, so assuming you see the value in a function like that display grade that is declared taking a reference to a parent class type, and then as a result, you can pass in objects of any of the child class types and have it call the right functions for each automatically, we can build on that idea and think about maybe pre-planning our class hierarchies for that purpose. And maybe we'll be sure to build a parent class at the top just for that purpose, just to have a common linkage between a whole bunch of classes. And maybe we'll set it up that we're not even interested in instantiating objects of that type. We're only going to use it as a pointer or a reference. So you can do that in C++. That's called having an abstract base class, where you have a class that serves as the basis for a class hierarchy, but cannot have any objects instantiated on its own. That's not the point. The point is just to provide a starting format for child classes to have a common pointer type that you can refer to all of them by, and to have a convenient target type for polymorphic function calls like that display grade function. And then later on, you can build out more child classes and know that you can use this parent class pointer type to refer to any of them. That could be pretty convenient. So if you want that, how do you make that happen? In your parent class, you have to give that parent class one or more what we call pure virtual functions. And that's a function that you provide the prototype for how you'd call it, but you've given it no implementation code for the compiler to compile yet. And therefore, that function must be overridden in a derived object class. Redefine the function, that's where you get the code, not in the parent class. And to signal to the compiler that's what you have, in the parent class prototype, right at the end of the prototype, you tag it with =0. And when the compiler sees that, it says, okay, I see the prototype, I know how you'd call this function, and I know you're not giving me any code for this. And at that point, the compiler won't let you make objects of that parent type. It wouldn't make sense, because if you had an object, there'd be functions you couldn't call because there's no code yet. So on the one hand, you can't make objects of that type, but again, you can make a pointer of that type, and you can give it the address of any child class object that you make later on. That's what we mean by an abstract base class. So if you think about that display grade function, even if you couldn't make graded activity objects, you could still have that function look exactly the same and send in any of the child class objects and have it work polymorphically. So that would still work in that case. Now, here's an interesting example of basically where the C++ standard library used something like an abstract base class to set up the object structures. And if you look in this is a UML class hierarchy diagram. It's kind of a small slice of the total I/O library in C++. If you look at the bottom here, hopefully you'll see some classes that you're familiar with. Like on the bottom left, there's ifstream, an input file stream. We've been talking about that since chapter 12, or it's actually back in chapter 5. We talked about it right at the end of first semester. Well, what is an ifstream? For starters, it's a child class of a class called iStream for general input streams from files from the network, from the keyboard. For example, SYN is an object of type iStream. It's a globally accessible object of type iStream. So you didn't know that, but SYN is one of those types of things. And what is an iStream? Well, that's a child class of a class called iOS for general stuff about the I/O system. And that's a child class of this top-level parent class in C++ called iOS base that has the most basic things about any kind of input-output stream object. Now, the interesting thing is that iOS base, you can't make an object of that type. The system is set up, it won't permit you. But what you can do is you can make an iOS base pointer, and you can give it the address of anything in the picture. Or you can make a function that accepts an iOS base reference, and then that function will accept anything in the picture because they all count as iOS based things. Even though iOS base itself, you can't make objects of that type. And if you look down the other side, under iOS, like one of the other child classes is OStream, a general output stream to send things to the network or a printer or the monitor. For example, Count, that obviously you've been using since day one. Count is a global object of type OStream. And then beneath that, there's a child class called OFstream. You know what that is. That's an output file stream. So a couple things here. This explains, one, what SYN and Count are. They're particular objects in this class hierarchy. And two, it also explains why it was so easy to transition from using Count to using OF streams like for text data. And in both cases, both COUT and an OF stream, you use the left-hand angle bracket to send some information into it, a number or a string. And the reason why that was so familiar, and the reason why it works so similarly, is that they are the same thing. An OF stream is a O stream, just like COUT is. They're literally the same thing, and so that's why it makes sense for those operators and those functions to work the same way. So convenient to build, and we could use our familiarity with one as an application programmer to use another one. It was very easy to get started with that. So I think that's kind of an interesting example about stuff you've been using since day one, and C++ set it up in advance as an inherited class hierarchy exactly for the purpose of polymorphic function calls. Okay, so this is the end of what I call part 3 of the course for us at Kingsborough. And my students will be getting ready for test 3 coming up pretty soon. And I would recommend to them, if they're going to get an A in the course as usual, they should read book chapter 15 in its entirety to see all the details there. They can test themselves with the review questions at the end of chapter 15. I will have a practice test version of that on our learning management system to look at. And as always, the gold standard to get good at this is more programming practice. So if you do have additional time in addition to our graded assignments, I could recommend programming challenges 13.1, 13.10, 14.8 in the book. Those would be great starting points to get extra practice. And then if you have more time than that, just other stuff in chapter 13, 14 would be great as well. And I would expect to get together with my students live for a lab activity pretty soon. I'd do something like go into the book's lecture code for chapter 15, go into the same folder that we used in this video for an example, look at one of the other applications, like maybe program 1514, and I would have my students read the specification changes there since we saw it last to test that program, and I'd ask them questions like, what do you think is going to be printed from this application? And what would happen if the virtual keyword was removed from the parent class specification? And hopefully that's good preparation for their upcoming test. Now, when we come back next time, we're going to start in on what I call part 4 of the course. And now that we know the major principles of object-oriented programming, like data hiding and inheritance and polymorphism, we can start to use those principles to build out other technologies that we call abstract data types that you use in larger kinds of programs. And that'll give us some nice advantages when we do that. One, it's going to give us additional practice at object-oriented programming, which is just super important. And two, it's also going to give us a preview in the kinds of work you do in future courses, building abstract data types. So I hope that you'll join me for that, and I'll see you then.